Hey guys, this is Monica and today I'm going to be going over problem 58 from chapter 18. The question here reads, the 50 kilogram circular piston shown in the figure floats on 0.12 moles of compressed air. Question A, what is the piston's height h if the temperature is 30 degrees Celsius? And part B, how far does the piston move if the temperature is increased by 100 degrees Celsius? Here in the figure we can see that we have the original container with the mass above it and the pressure of 1 atm. And this is at the temperature of 30 degrees Celsius. And given by the problem, we know that the amount of moles inside is 0.12 moles. And the goal for part A is to find what this height is. And for the second part, we know that there's an increase of 100 degrees Celsius, which gives us the final temperature of 130 degrees Celsius. And this here is not drawn to scale due to the lack of space that I have. But our goal is to find how much the displacement is from the original height to the final height. So for part A, we are obviously going to be using the ideal gas law of PV equals nRT, and we are going to want to go through each variable and fill in what is the information that we're going to plug in. So first, starting with the right side of this equation, given by the problem, we know that the amount of moles is 0.12 moles. R is always the same. And in this case, we are using the 8.31 joules per mole times Kelvin. Temperature given is 30 degrees Celsius, but we need it in Kelvin, so just simply add 273 to convert it to Kelvin, and we get 303 Kelvin. And for our pressure, we know that we have the pressure of the atmosphere plus the additional pressure given by this mass on top of the air. And the way we solve for this pressure of mass is the mass times gravity over the area. So to solve for the area, area is pi r squared, and given here it's 10 centimeters, but we need the radius, so we're going to divide that by 2. So our area is going to be pi times 0.05 meters squared, and we get 7.85 times 10 to the negative 3 meters squared. We also know, given by the problem, that our mass was 50 kilograms and gravity acting on the mass is 9.8 meters per second squared. So simply plugging all these values in for the pressure, adding it to the atmospheric pressure, we get that our pressure is going to be 1.63 times 10 to the 5th pascals. Next, we're going to be looking at the volume, and the volume is what's going to help us find the height, because we know that the volume is width times length times height, and width times length is the area, so we're just going to plug it into our equation as area times height. And if we rearrange this so that we have the height solved for, and then simply plug in all the values that we have described, we get that the height when the temperature is 30 degrees Celsius is 0.24 meters. Now for part B, we have a change in temperature of 100 degrees Celsius, so our final temperature is 130 degrees Celsius. Converted into Kelvin, we get 403. And using the same format, we get that the second height is 0.31 meters, but this is not the height that we are looking for part B. We are actually looking for the displacement. So we have this total height subtracted by the initial height, which was the 2.4 or the 0.24 meters. We get that the displacement of height was actually 0.07 meters or 7 centimeters. So in conclusion, we know that this problem is an isobaric problem, meaning that there's no change in pressure. And the reason this is an isobaric problem is because even though the temperature increases and we're inclined to think that the pressure will also increase, since the volume also increases, it kind of makes the pressure stay the same. And even though pressure and temperature are directly related for fixed systems, this is not a fixed system. So the temperature and pressure will not be directly related.